Here is an introduction to galaxies and dark matter to accompany chapter 28 of the textbook Astronomy from Open Stax. So dark matter, what do we mean when we say dark matter? So matter just means stuff with mass. So by that we mean something that interacts gravitationally. It seems to account for around 85% of all matter in the universe and about 25% of the energy matter content, and we'll talk about some evidence for this in a moment. And what do we mean by dark? Dark means that it does not absorb, reflect, or emit light. And you might remember when we talked about the Milky Way, we believe that there's a halo of dark matter, so kind of just a spherical dark matter blob that the galaxy is basically embedded within. And talk about it at the end. The most likely candidate here is that some kind of new particle that we don't know about. So what's some evidence for dark matter? There's a lot of evidence for dark matter. I'm just going to give you two examples that are related to galaxies. There are more pieces of evidence for dark matter and actually even more related to galaxies. But let's go into a couple examples. So one is so-called galaxy rotation curves. So if you have a small object orbiting a massive object, like a planet going around a star, then Kepler's laws of planetary motion apply. And Kepler's third law is that the period of your orbit squared is proportional to the semi-major axis cubed. So we say that t squared is proportional to a cubed. And if you're talking about a circle, then this a is just r, the radius. And if we take a look at objects in our solar system, these are planets, they're small objects going around the sun, which is a massive object. We can measure their semi-major axis, just sort of the radius of the circle, measure the period, so how long does it take to go around to make one orbit, and we plot here the radius cubed divided by the period squared, and you see it's more or less constant. It's more or less the same number, exactly like you would expect from Kepler's third law. And if you're thinking about a galaxy, then a star is a relatively light object compared to the galactic bulge, which is a very massive object. And so you'd think that Kepler's third law would apply there. And so then let's take this a little further. For a circular orbit, you know our semi-major axis is just a radius. The circumference of the orbit that you're taking is 2 pi times the radius. Right? That's just the formula for the circumference of a circle. That is, by definition, covered in your period t, so it takes one period to go a full circumference. And so then the velocity is just going to be the distance covered divided by the time. Okay. So we have Kepler's third law that we have that our period squared is the radius cubed. So in place of the period here, we can put in the radius. So we take the square root of both sides of this equation, and we get then that the period is proportional to the radius to the 3/2 power. And so we plug this into our equation in place of the period, and we won't worry about the constants. We'll just use a proportionality symbol. And we see that the velocity then is proportional to radius over radius to the 3/2. This is a power of +1. This is -3/2. We take the difference and we get -1/2. And so the velocity should go as 1 over the square root of the radius. So when I look at stars at different distances from the center of the galaxy, this is the kind of velocity versus radius dependency that I expect. However, when you take a look at galaxies, this isn't what you see. So here we're looking at the galaxy M33. This is a nearby galaxy in our local group. And this is a visible image here. And what's plotted here is the distance from the center, the galactic bulge, along the horizontal direction, and then the velocity of stars that we see at this distance. You'd expect something that follows this 1 over square root of the radius. Once you get outside of the center of the bulge, you'd expect that fall off. And yet when you measure actual velocities, you see it's not decreasing, if anything, it's increasing, right? So in order to have this happen, you would need an extended matter distribution, right? So for our galaxy near the bulge, this approximation of having a massive object and a small one near it doesn't quite hold, right? You have a lot of mass around, and so near the bulge you have something that kind of goes up still. And so the idea then is that there's actually a huge dark matter halo, and we're just not far away enough from that. In fact, we're still embedded within it, and that's why the velocities don't decrease as 1 over the square root of the radius. And so to picture what this looks like, here is just a calculation of what the stellar velocities would look like if you did not have dark matter. You see orbiting very fast near the center and slower the further you get out. If you add dark matter, then when you get to far radii, you see that these stars are basically circling. So this one here at an inner radius and this one at an outer radius, they're more or less circling at the same rate. And we can look at lots of galaxies. So this is a survey of a bunch of dwarf galaxies. And you're looking at the normalized velocity as a function of the normalized radius. And you see they all kind of follow this curve here. The stars are a simulation, but all of the other symbols, these are observed properties of the galaxies. So it seems like galaxies have dark matter halos. We can also get evidence of dark matter from gravitational lensing. So before I show you how that is, I need to describe what gravitational lensing is. So when light travels through space-time, the path is warped by a massive object. So we can think of space-time as this fabric. Any massive object is going to create a dimple in the fabric. The more mass of the object, the bigger the dimple. And light traveling is going to follow one of these lines, and these lines are curved by a massive object in space-time. And so the bending of light can cause what looks like multiple copies of a background galaxy warped into arcs. So in this video, what you're seeing is you have a background galaxy, a foreground galaxy, and your telescopes, and the light is actually warped through space-time by this foreground, and then what we see, instead of this background object, we see some arc of light. So we can see multiple copies of the galaxy. If the alignment is just right, we can see a ring. There's lots of different things that can happen due to gravitational lensing. So this is a really cool image of a galaxy cluster lensing distant galaxies. And the point here is not only that this looks really cool, but that you can actually use gravitational lensing as sort of a magnifying glass to see very distant objects. So the bright objects here, these bright yellow orbs, this is a galaxy cluster. As amazing as that is, these are all a bunch of different galaxies. Together they're a cluster. And their mass is warping space-time, and these blue streaks that you see, these are actually very distant galaxies. And these are some yellow streaks here. These are very distant galaxies that are somewhere located way back behind this cluster, and their light is then bent, and we can see it. And it's sort of like a magnifying glass, so you can use this as a tool to see further away, dimmer objects than you would otherwise be able to see. So then we can, so what does this have to do with dark matter? Well, that means we can use gravitational lensing to actually measure the mass of objects. So what we can take a look at is you have, for instance, these two merging galaxies here that are nearby. There are galaxies in the background. If you were to zoom in really close on these, you'd see that some of these ones in the background are stretched or warped a little bit. You'd see that their light's actually lensed a little bit. And the amount of lensing is going to depend completely on the mass of this object here. So this particular object is a so-called bullet cluster, and gravitational lensing has been used. It was actually by an OU faculty member, Doug Clow, right before he came to the university. He used this gravitational lensing to determine the mass distribution of the bullet cluster, and that's the blue orb that you see here. Then we can look for actual light output from these colliding galaxies, and that's X-rays. And the visible matter, then, that's in the pink. And so you can see that these two things are actually separated, and this is extremely strong evidence that dark matter exists. There is other evidence that dark matter exists from galaxies alone. So you can, for instance, get the mass of a galaxy, of a galaxy cluster, rather, by looking at the relative velocities of galaxies within the galaxy cluster. That's one way to do it. And so you have at least those two, or those three rather, methods, and there are more, but the simplest ones to understand are you have galaxy rotation curves, you have gravitational lensing of clusters, and you have the velocities of galaxies within galaxy clusters. So just to wrap this up, okay, then fine, we see that there's dark matter. What is dark matter? And the bottom line is we don't know. Nobody knows. If someone tells you that they know, they're not telling you the truth, or some major discovery has happened between February 2021 and now, because I don't know when you're watching this. At the moment, we just do not know. But it's not like we don't know anything. We can say the following things about dark matter. We can kind of constrain what it could be. So it's probably not just black holes. So you remember that the definition of dark matter is it just has to not be luminous and it has to be massive. And a black hole fits that picture, right? And there are a handful of compact objects that are massive in the universe that would fit that definition. So people lump these into MACHOs, massive astrophysical compact halo objects. And it's unlikely that these are the explanation, partly because the Big Bang just didn't make enough regular matter. It would ruin descriptions of the Big Bang that otherwise work quite well. And then the fact of the matter is we just don't see enough of these. You would think that you'd see these black holes kind of floating around your galaxy, and there just aren't enough to account for the amount of dark matter that we need. So probably it's not those. It's probably not neutrinos. So again, dark matter is matter, something with mass, and dark, it doesn't interact electromagnetically. Neutrinos are really light particles. They interact via the weak force, so they're made in radioactive decay, for instance. And so in principle, they could kind of fit the definition of dark matter. Maybe there's just a lot of neutrinos, or even a new neutrino type. The issue is that because they're so light, they move really fast. And at the beginning of the universe, they would be moving very fast. And so they would kind of smear out your matter distribution, and you would expect huge galaxy cluster-sized groupings of matter to form first, and then galaxies to coalesce within the clusters. And when we look back into the history of the universe, that's just not what we see. We see kind of galaxies forming and coalescing into clusters. So neutrinos don't really fit the picture very well either. You might have a bright idea and say, wait a second, maybe the theory of gravity is wrong. You probably know that Newtonian gravity was supplemented with general relativity, just based on in the early 1900s, seeing that we needed an extra theory of gravity to explain some observations. Einstein came up with general relativity, and it works really well, and you need it for things like GPS. So maybe we need to add another layer on top of this, or it's really a more complicated description of gravity. So one name for this is modified Newtonian dynamics, and the problem is just none of these theories work. There are lots of observations of dark matter, just covered a few here, and no theory of gravity works for that, so probably not that. So the favorite is something called cold dark matter, and so the idea is it's a new particle. We call it cold just because it has to be massive enough that it's not really fast moving. And that's basically the constraints we have on it. A lot of researchers are attempting to detect this, and so the idea is that some theory proposes a dark matter particle, like axions are one, weakly interacting massive particles are a whole category of another. And then based on the assumptions of the properties that dark matter particle would have, experiments are designed to look for this. So for instance, you can use a particle collider and try to, you combine two, for instance, protons together, and that creates a lot of energy, and that'll make new particles. You can combine these together at different energies, and you scan that, and potentially you'd find a new particle by doing that. Another thing you can do is you can set up a detector that is made to basically only detect a particle coming in and colliding with your detector material. And that's extremely challenging. Those detectors exist as well. And so far, no one has come up with anything that actually works. So we really, we know what dark matter isn't, but we still don't really know what it is. And that is it for this introduction to galaxies and dark matter.